so tomorrow I should be able to give back your quizzes and all the homeworks up until the assignment you're working on now. The assignment you're turning in tomorrow, take pictures of it before you turn it in if you want to be able to look at it while you're studying, because you won't get that one back until after spring break. But all the other stuff, you should get it back tomorrow, and so you'll be able to study from all of that. So yeah, so the review session questions that I posted, of course, that's what I was going to go through tonight. I might make a couple of changes because I realized one of the problems I had actually already done in class, so maybe I'll just change it to a different problem. So that's kind of going to be what I go off of. But just to give you a quick breakdown, of course, chapter 4, we're going to be talking about 4.1 through 4.12, except 4.7 you can skip. We're not going to cover that. That one section is going to be left off. And then I would say that whole chapter would be maybe 80% of the midterm at least, maybe even more than that. Almost the whole midterm is on chapter 4, and even chapter 5, the one section of chapter 5 is kind of related to it anyway. So over here I'll just put chapter 5, and only 5.1 is going to be on there from chapter 5, so not very much. This would be maybe 20% at the most of the test. So that's a fairly small chunk of it, and some of you haven't even quite learned that stuff yet, so that's all right, because we'll cover it tomorrow, and you'll be good to go. It'll be fresh in your mind. It's not that bad. So I think it'll be okay. So in chapter 4, of course, I want you to know, I'm just going to give you a brief outline here before I do any of the problems. Of course, you want to know, you need to know all of the familiar vector spaces. So somebody tell me, what's like an example of a very familiar vector space? M of n for all of them. Mn of R, okay, n by n matrices. What's another example? Rn, that's a good example. What else? Pn of R, that's a good one. What else? C of A, the space of functions, exactly. We talk about calculus functions a lot. That's another good example. And the only other one that's sort of in our standard family would be the matrices don't have to be square matrices. So you could even talk about M by N matrices as well. So these are like the standard examples of vector spaces. Now within those vector spaces, we have lots of examples of subspaces. Okay, so subspaces are within there, and everybody needs to be able to show, as I asked you on the quiz, the two main steps for subspaces are closure under addition and closure under scalar multiplication. And so you want to be able to check if those properties are true or not for any given example. And along with that, the other thing that we sometimes do with subspaces is we check the zero vector. So zero vector check. The reason for that is that if there is no zero vector in the set, then you know that you don't have a subspace and you can stop right away. You don't have to spend so much extra time working on that. But if the zero vector is in the set, well, then checking closure under addition and closure under scalar multiplication would be the next thing. I almost certainly am going to ask you a question on when I'm not giving anything surprising away, or will almost certainly ask you about subspaces on Wednesday. And you know, you need to practice this because it's important to have an idea. If I give you a vector, if I give you one of these 5 vector spaces, and then I give you a subset of one of them, then you need to have a feeling. Do I think that it is a subspace, or do I think that it is not a subspace? Because which way you go with it, the way you proceed depends a lot on whether you think it is or isn't a subspace. So we're going to practice. We'll practice this tonight as well to kind of review it. But you know, there are some subspaces that are especially important. Anytime you take the null space of a matrix, that's an example of a subspace. Another one is the row space of a matrix. and the column space of a matrix. These are all subspaces, for sure. And do you guys remember if A is an M by N matrix? Let's say A is M by N. Can you remind me, the null space would be a subspace of what? Of which of my vector spaces up here? The null space of a, so the null space of a matrix, it's the set of which, it's the set of vectors in which vector space? R what?
R of N.
N, right? N, yes, exactly. This is a subspace of Rn. Good, subspace of Rn. By the way, guys, somebody was emailing me over the weekend with some questions about this, and they said, oh, the null space is a subset of Rn. You sometimes see the word subset written down. Subset is not the same thing as subspace. Subspace is a stronger word. If I tell you that something is a subspace, of course I mean that it has these closure axioms satisfied. So be sure to say subspace when you mean subspace. Okay, so the null space is a subspace of Rn. What about the row space of the matrix? That's a subspace of what?
Of
Rm? I don't know why mathematicians don't use two different letters. I have to make sure I can hear the letters correctly. What is Rn? Yeah, this is also a subspace of Rn because each row has n entries, right? So subspace of Rn. Okay, so Nick, column space of A. It's a subspace of
Rm.
There we go, Rm. So subspace of Rm. That handout that I gave you guys about a week ago, that was like the big page-long recap summary page, whatever. That is a really, really handy handout. I actually, when I wrote it up, I was kind of not thinking it was that big of a deal, but then after I printed it out, I was like, wow, this is really good. I should use it every semester. So if you lost that handout or you need another copy, let me know. That's something you should totally master, that page. And it includes this stuff on it. There's actually a nice table that talks about this. So yeah, null space, row space, and column space. Those are examples of subspaces. Okay, I'm going to erase over here so I can keep talking a little more about chapter 4. The next big chunk of concepts in this chapter would be the spanning set stuff, the spanning sets, and the linear independence, linear dependence stuff. Those two topics. So if I give you a set of vectors, okay, so I can kind of put these together. I say, given a set S inside of V, so V is your vector space. So if I take a vector space V and S is some set inside of it, I can ask, is S a spanning set? Is it Li? Is it both? Or neither? This is another type of question that, I'm very likely to ask you something like this. You need to be able to handle questions like that in any of the vector spaces. So I might give you some polynomials and ask you about a subset of polynomials. Then I might give you matrices, would be a different example, right? So you need to be competent and comfortable with how to answer this question, not just in R3 or R2, but in any vector space that we could work with. I probably on the test will be mixing it up a little bit. There'll be one problem where I ask you about polynomials, and there'll be another problem where I ask you about Rn, and so on, because I want to know that you're comfortable with all of these different examples of vector spaces. Okay, so these kinds of questions you want to be able to address. The general strategy for working with these, of course, this is also summarized on your handout. If I let S be equal to the vectors v1, v2, up to vn, I have those vectors like that, then what you end up doing from a practical perspective is you put your vectors into the columns of the matrix and you augment it either with 0 or with numbers, right? And you put zeros here when you're trying to address which question? The LI, LD question, right. So if you're asking are the vectors LI or LD, you put this column of zeros at the end of it. If I'm asking whether the vectors span V, then what do I put in that last column? Right, these arbitrary numbers here. So exactly, the thing I just wrote is like a number symbol with a vector on it. So you essentially do both of these questions by the same process. That is, you row reduce the matrix that has columns given by your vectors. So you put your vectors into the columns of the matrix, and then you simply row reduce it, and it'll be the same row reduction process, whether it's this zero or numbers there. So you don't actually have to do it twice. You don't actually have to do it twice. So that's kind of nice. And just remember the whole bit about, if you know the dimension of V, if you already know in advance what the dimension of V is, well then if I give you more than that many vectors, then they can't be Li. And if I give you less than that many vectors, then they can't span the space. Right? The only way they have a chance of spanning the space and being Li both, the only way it could be both is if I give you exactly the right number of vectors. In other words, whatever the dimension of the space is. So make sure you, okay, that's getting to the next point. Basis and dimension. Make sure that you know the dimensions of all of these vector spaces, right? Let's just come back here really quick. The dimensions of these spaces. So what is the dimension of the n by n matrices? N squared, okay, good. So I'm putting the dimensions here. What's the dimension of Rn? Just n. Just n. For n. For Rn, it's just n. What's the dimension of Pn of R? That's n plus 1. Okay. What's the dimension of the functions, continuous functions on the interval AB? I didn't really go over that. The answer is it's infinity. It doesn't have a finite dimension. I can write as many arbitrary linearly independent vectors as I want, and I'll never run out of vectors. So this is not an easy vector space to really work with in terms of studying the dimension. Okay, but what about the m by n matrices? Good, m times. So you want to know all of those numbers. Okay. Now, of course, a subspace also has a dimension because a subspace is a vector space. So things like this, these vector spaces down here, they also have dimensions. It's just I can't tell you numerically what that dimension is. It depends on the matrix, right? So the dimension of the null space, we call that the nullity of the matrix, right? So the dimension here would be the nullity. The dimension of the row space, what would that be called? The rank, exactly, the rank of the matrix. So this one would be the rank of the matrix. What about the dimension of the column space? Also the rank, very good. So all of this is on that handout, right? So you just pull that handout up, it's gonna be there for you. So that's, so you wanna know those things. Or I can give you some other subspace and say, well, what's the dimension of it, right? So some dimensions we know in advance. All these ones I just listed here. If we know the dimension in advance, then we should have an idea when somebody gives us a handful of vectors, whether we can rule any of these four choices out, right? Spanning set, Li, both, or neither. If I give you the right number of vectors that matches the dimension of the space that you are given, well, then you know it's either both or neither. But if I give you too many vectors, then they can't be a basis because they can't be Li. And if I don't give you enough vectors, which is like the one I gave you on the quiz on Wednesday, if I don't give you enough vectors, then they can't possibly span the space. Right? So, okay, so we just want to make sure everybody's good with all of that. We'll have to practice this a little bit tonight. What else? Oh, the rank nullity theorem. Everybody needs to know that one for sure. It's a very, very simple theorem. As you remember, this just says that the rank of a matrix, which is just the number of pivots in the row echelon form of the matrix, plus the nullity of the matrix, which is just the nullity of the matrix is just the number of free variables when you've row reduced your matrix and you're solving it by back substitution. You're solving the system by back substitution. So actually, the number of free variables is just the number of unpivoted columns. So you have number of pivoted columns plus the number of non-pivoted columns, right? And all that this theorem is saying is, oh, that adds up to all the columns of your matrix, and you have n columns in a matrix. So this is not a very deep result, but it's kind of nice to know it. And you'll remember we did those problems where I said things like, well, suppose that A is a 5 by 7 matrix and the nullity is 4, right? Then what would the rank be? Or another question would just be, suppose it's a 5 by 7 matrix, what could the nullity be? Like what range of values could the nullity be? And the homework problem that you did, you showed that the nullity had to be between 2 and 7 in that assignment. So being able to use this theorem for things like that is kind of helpful. Okay, so that's that. Then we have the invertible matrix theorem. We revisited that. We didn't do any homework on it, and basically the reason why it's worth looking at that also is, I mean, I don't know exactly what kind of question I would necessarily ask you on it, but it's just helpful to read those statements in the invertible matrix theorem and to ensure that you have a good conceptual understanding of the stuff. If you can kind of go through those statements and say, yeah, that makes sense. Okay, an invertible matrix, it obviously has a nullity of 0 and a rank of n, for example. Okay, and it fits with this equation. We know, what else do we know? The columns of the matrix will be Li. The columns will also be a spanning set for Rn, right? Therefore, the columns are a basis for Rn. And then same thing for the rows of an invertible matrix. Remember, an invertible matrix is going to be a nice square n by n matrix, right? So you're going to have like n columns in Rn. It's the right number of vectors. So you end up in this, basically for an invertible matrix, you get a both conclusion here. The columns are both a spanning set and they're linearly independent. Same thing for the rows, right? By the way, you always want to think about an invertible matrix as being like a good thing. It's a good thing, then you think, well, what else is a good thing? Well, the other good things are linear independence is a good thing, and spanning set is a good thing. These are all good, so they all go together, right? They're either all true or they're all false about a given matrix that you're looking at. Okay, so that's that. And then just the very last bit here from chapter 4, and just interrupt me with questions as we go along if you have any. Very last thing from chapter 4 is just the inner product stuff that you guys just finished up with. So inner product spaces. So just what you want to be able to do is you need to know the 4 axioms and be able to check them. So you want to know them and be able to check them very, very easily. And you want to be able to compute the inner product of 2 vectors, the norm of a vector, the angle between 2 vectors, some of these geometric concepts. So you did this in the homework that you turned in on Friday, which you will get back tomorrow. You calculated some of these things, the lengths of some vectors and so on and so forth. So those are some good things to be able to do. And then you want to understand the normalization process, where you take a vector. Okay, so this is where you take a vector and you turn it into a unit vector by just dividing by the norm of the vector, right? So we can shrink vectors down so they have length 1. And then finally, the part that we just did at the end of class last week is the Graham-Schmidt process. Gram-Schmidt process, okay? I really recommend that if you have not started the homework for tomorrow, that you at least, just so your life tomorrow isn't really, don't get you stuck here till 10 p.m. at night, I would get the 4.12 problems on the Gram-Schmidt process done. That way you only have chapter 5 to worry about tomorrow. That would be the best thing that you could do. These don't take that long. I know a lot of people who are already done with 4.12. So if you could put yourself in that category too, that would be really nice. That way you don't have so much to worry about tomorrow. Okay? So I'm going to give you the Gram-Schmidt formulas on the test. You don't have to memorize those. They'll be right on the front page of the exam. But you have to know what it's used for, so that you know when to use those formulas. This is used to make an orthogonal basis for something. So you're trying to, the idea is you have some vectors that are not orthogonal, and what you do is you replace them with vectors that are orthogonal, perpendicular to each other. Okay. Having an orthogonal basis is a nice thing to have. You like having vectors that are perpendicular. They are computationally simpler to work with. More about that in Math 307. But the procedure of it is very simple. So you just use those formulas. So in terms of concepts, it's not so conceptually challenging as some of this stuff. Okay? Is that okay with everybody? So far so good? Okay. And then just really quickly, I'm going to tell you what the chapter 5.1 is about, and then we'll come back to it later. But basically, there's not much there. In 5.1, the main thing that is going to be in that section is just basically you're going to be talking about transformations, which we're usually going to denote by a capital T. And these things go between two vector spaces. So these are like functions. So you have V, which is where your inputs come from. Your inputs are coming from V, and your outputs are coming from W. Okay, so you input whatever these vectors look like, and you output whatever these. So these could be, the inputs could be polynomials, and the outputs could be matrices. Right? Or V and W could be the same vector space. That's also allowed. So it's just you have two vector spaces here. It's almost like, it's just like a function, right? You're taking things from one side and mapping them to the other side, right? It's just looking at how things move across from V to W. And given a function like that, the main question that I will be asking you is T linear? That's going to be the main question. And what that means, simply, and again, I'm going to go over it again tomorrow. I'm going to go over it in those videos if you want to watch those. Basically, linear just means that T has to respect addition. What I say, in this case, I say T respects addition. Okay, this means if I add two vectors together first and then transform them, I'm supposed to get the same answer as if I transform them separately and then add the results. So the question is this true? And does T respect scalar multiplication, which I write like a dot? Okay, this one would be T of K times V. K is my scalar, right? If T respects scalar multiplication, you have to be able to pull the constant K out of the transformation. So the one thing we need to get a little bit of practice with between now and Wednesday is verifying these two things. Okay. So if I say is T linear, it's just like subspaces. There's two parts, right? There's an addition part and there's a scalar multiplication part. They both have to be true in order for us to say yes, it's linear. If either one of these two parts doesn't work, then it's not linear. So we'll practice this in a little while. We have to, somebody has to give you the formula here. Like, how do I take inputs and how do I map them to out? I have to tell you what V is, I have to tell you what W is, I have to tell you how to go from V to W. All of that has to be given in the problem. And then the only thing left for you to address is, do these properties work or not? So it's not actually that bad. We do have to write it up. It almost feels like checking closure under addition and scalar multiplication. So you have to write some things out. But it will look familiar to you from that closure under addition and scalar multiplication thing that we did before. So that's what 5.1 is going to be about. But we'll practice that a little bit. Any questions on the overview? It's just an overview. Now we're going to get into some of the problems. Okay, I'm going to stop this for a second.